what, 3 weeks? Is that right?
Wait, so are we taking our exam before?
So, but we're done. So when you come back after Christmas break, you'll have your new schedule. We'll be in new classes. I don't know because we have to have grades in before we can leave for Christmas break. Okay. I don't have time to grade a project. But listen, from here on out, what we are going over, we are going to focus heavily on trig and things that I know that those of you who are taking, and I know that everybody's not taking calculus, but this is pre-calculus to prepare you for calculus. So we will be focusing on things that really the calculus students have struggled with over the past few years. And a lot of that happens to be trig. So we're going to talk about trig identities, and unfortunately, these you just have to memorize also. Yay! Yay! You have to be able to recognize them. These come into play a lot in calculus, and it is always a struggle because students do not remember them. So these are things that we could go through and prove. I'm not going to take the time to go through and prove them. Unless you just want me to, in which case I can, and I can show you why they work, or I can just tell you that they work and you know they work and you recognize them. It's kind of like the Pythagorean theorem. You could take a quadratic formula equal to 0 in standard form and you could complete the square and get the quadratic formula, but I lose you on all that, and then I just give you the quadratic formula until you memorize it. You do a little bit better with it. So, y'all ready? All right, let's talk about some ones you already know. Let's talk about the reciprocal identities. Again, these are all coming back to sine, cosine, and tangent. You don't have to know the names of them. Reciprocal trig functions that you already know. So in other words, cosecant theta is equal to what? 1 over sine of theta. That's exactly right. How about secant? 1 over cosine. And how about cotangent? 1 over tangent. I could also say that this is cosine over sine. Now, with this in mind, I could also write this the other way. I could say that the sine of theta is equal to 1 over cosecant theta. I know, it's a lot. It is a lot. The cosine of theta could be written as what? 1 over secant theta. Well, if you get into what we're going to be doing is reworking some trig things, and if you happen to see this, you would know that you could replace that with just sine theta. You want me to show you why? These are easy to show why. 1 over cosecant theta. What did we say cosecant theta was? 1 over sine, right? Instead of dividing by a fraction, I multiply by the reciprocal, and I come back to just sine theta. That's what I meant by showing you how they work and why they work. Or I can just give it to you. These I can remember in trig in high school and in calculus having these identities on flashcards and just memorizing them. And it stinks, but And then, of course, we're missing tangent theta, which is 1 over tangent theta. None of these are really new. You might not have thought about it this way. Oh, yep, sorry. Brains lagging a bit. And then, of course, we know, and these are called quotient identities, and I kind of already incorporated one of them. Identities. That the tangent of theta is equal to what? That's right. Sine over cosine. And the cotangent is equal to cosine over sine. The flip of that. That's exactly right. I know this is boring. I'm just kind of laying them out there for you. All right, y'all ready? Those long ones are quotient math. Now let's talk about some ones that you haven't seen yet. These are probably the ones that show up, these three show up the most. They are the Pythagorean identities. I'm going to give you, there's three of them. I'm going to give it to you, and then I'm going to work through an example or two and show you how we use them. And then before we move on to the others. All right, so I told you three. The easiest one to remember is sine squared plus cosine squared equals 1. Okay, now we could rework that. We could say that this is the same thing. Sine squared equals 1 minus cosine squared, or cosine squared equals 1 minus sine squared. If you see any of those anywhere. The second one is 1 plus tangent squared is equal to, bless you, secant squared. And then the last one, the cotangent squared. Notice all of these are squares. Plus 1 cosecant squared. All right, you ready to use it? Y'all please be a little more excited. No, I'm just going to break from right here and do an example with these and come back. Would you rather me just list them all out first? They get kind of, these are the easy ones. After this, it kind of, I know, I'm sorry. And we may not do all of them today. There are 3, 6, and 12 more. And I don't think we're gonna prove them. That's why I said, would you rather me just 12 more identities? Like this is 3. Yeah, the other one you had what? 2, 4, 6, 8. Yeah, so about this many more. Let me show you an example, and then we'll do some more identities. Let's say that I told you that the tangent of theta is 5. Could you find sine theta and cosine theta based on this? And I will tell you that cosine theta is going to be positive. What could I possibly do? Okay, so you're saying use this. How is that going to help me? You're actually on the right track. All right, Kirsten says use this one. And let's plug in what we know. Well, we know, and by the way, when you see this, it's the same thing as this. I think we've talked about that before, haven't we? We talked about that in here. I start getting confused on first and second block on what we've talked about when we hadn't. Tangent squared is the same thing as tangent theta squared, squaring the whole thing. So what do we know? What is this? 5 squared, right? We know that because we know tangent theta is 5. So we've got 1 plus 5 squared equals secant squared theta. You all okay there? Okay. So this would be 26. So what does secant equal? The square root of 26, right? So the square root of 26. Now remember, I'm in a plus or minus situation here. How is this helping me? Remember initially what I need to find. I need to find sine and cosine. Okay, I can flip it. So secant is the same thing as what? Look at y'all using that reciprocal, and you didn't even know. Now what? It's got to be positive. You're exactly right. So what does that tell me about this? Right? Because initially it defined cosine being only positive. Okay, now what? That's exactly right. That's what cosine is. So use that property. We've talked about this in here briefly, where if you need to solve and you can't the way it is, you can flip both sides over. So you can say 1 over the square root of 26 equals the cosine. Well, that's one of the things I had to find. I still need sine. What can I do? Use the first one. What first one? So sine squared plus cosine squared. And you will find that there are multiple ways to do this. And Henry says do it this way using that very first Pythagorean identity. I know cosine and I know tangent. Cosine is 1 over square root of 26, so if I square that, and what's tangent? What was tangent? It is. I'm sorry. Steady working it. And God. I'm thinking ahead to how I was. Doesn't matter. Now solve it. If I subtract 1 over 26, that leaves me with what? 25 over 26. That's still not sine theta. What do I have to do? Square root? That's exactly right. Did anybody look at this and think of a different way? What'd you do? Okay, you could. Oh.
Wait, so one over.
Subtract 1 over 26, so 1 minus 1 over 26. 26 over 26 minus 1 over 26, which would give you the 25 over 26. Okay, so you made a triangle. Is that right, Khalil? Or you thought about it being opposite, adjacent, and hypotenuse and all that. Okay? Anybody else do it a different way? Or think of a different way to do it? What did we start with knowing? Tangent. What's another way to write tangent? If we know cosine, 5 equals sine over, right? And I could just multiply both sides by this. Either way, the point I'm getting to is there is not going to be a right or a wrong way to do these as long as you follow. And I know that y'all hate that because that's whenever you start floundering because you just want me to tell you the exact way to do it. And there's not always just an exact way to do it. And you can see I come back to this. Yes or no? It's just working with them. That's exactly what we're doing. Y'all want to do one more example before we do any more?
Wait, 12 more properties or 12 more Pythagorean Identities? 12 more like identities.
No, they're not Pythagorean. What I'll probably do. Oh, no. What I'll probably do is lay them all out today, give some easy kind of work tonight to practice with them, and then we'll practice with all of them tomorrow again. I plan on spending 2 days on the properties, on the identities. Go ahead and tell you the identities. Okay. All right. Before I do more examples. All right, so those were the Pythagorean identities. Do you see how we're kind of going to use them to work together and do things, though? Does that help you understand where we're going with it? All right, my least favorite ones. The cofunction identities. Here's when we start getting into some specific values identities. I'm not going to go into why or how again. I'm just going to give you the identities. There are 6 of these. The sine of pi over 2 minus theta is going to equal the cosine of theta. if you think about this in terms of the unit circle, it makes sense. Wherever I am on the unit circle, how far is pi over 2? That's a quarter of the circle, right? A whole quarter of the circle. Anywhere that I am on the circle, if I go a quarter of the way, the x and the y switch values. Okay, so that's why this works, the pi over 2 there. So then the second one here is the cosine pi over 2 minus theta is equal to the sine of theta. That's just the angled measure, yep. It could be pi over 2, it could be pi over 4, it could be pi, 30 degrees, whatever. We're going to stick in radians since pi over 2 is already in there in radians. So those are easy. Then we have the tangent of pi over 2. And it's actually going to equal the cotangent, so it's the reciprocal. And the cotangent the secant, remember, is 1 over, if secant is 1 over cosine, what do you think this is going to equal? You're exactly right. You are on it today, Kirsten. Cosecant theta. Okay? Remember, these are opposites, so these are opposites. That's all it's doing. And then, of course, the cosecant. What do you think that one's going to equal? Secant. Last 6. They're the easiest. Y'all got that? The even odd identities. Uh-huh. If you negate theta inside there, so the sine of negative theta or the sine of negative x, you will get negative sine x every single time. The sine of negative pi over 4 is the same thing as negative sine of pi over 4. Does that make sense to you? If I go negative pi over 4, the sine is negative square root of 2 over 2. The negative sine of pi over 4, negative square root of 2 over 2. So it just negates the value there. So you can switch those off. Cosine does not, however. It keeps its sign the same. So the cosine of pi over 4 is the same thing as the cosine of negative pi over 4. They're not the opposites. And the tangent will also negate the tangent value. No, it does not make it negative. It keeps it the same. Okay, so on your unit circle, if you went to cosine of pi over 4, and actually let's go to negative pi over 4. So I'm going down, right? What's the cosine of negative pi over 4? Well, back to my unit circle, if I go down pi over 4, cosine is square root of 2 over 2. It's the x, right? So it doesn't change. It's the same thing as it being the cosine of pi over 4. 3 more. Cosecant involves the sine or the cosine? The sine. So what do you think this equals? Negative cosecant x. You see how you can use some of them? Really, there's not 6 of them. There's 3 of them. You're using those 3 to make the cofunction ones. So then the secant of negative x, what do you think that equals? Secant x. And how about cotangent? And that's all of them for today. So now we just work with them. Use them to help us simplify and manipulate some trig functions here. Y'all ready? Y'all need a second? Yep. Simplify. Use your trig identities. Which basically means get it in a form that is not quite as involved. Okay, it looks a little bit different. Do you see, what do you see right off? Let's talk our way through it. The sine and cosine are connected, they are. In terms of identities, which one do you think you could make this one possibly look like to simplify it a little bit? I think so too. I think maybe I could make this one look like sine squared, cosine squared, because I've got 3 sines here and I've got the 2 cosines. The problem is this being hooked here and then there's 3 of these. Is there anything I could do?
Could you just like make a sine of 4?
Divide by sine x. The way you're thinking is going to go, but I can't just divide by sine x. It still needs to be there. So maybe I could factor it out, like a GCF. Does that make sense to everybody? So if I took a sine x out from both pieces, what would it leave me in the first term? Plus, well, what does it leave me here? You still got that cosine squared x. Now, this looks like the Pythagorean identity, right? And anytime I have sine squared plus cosine squared, what does it equal? 1. So I have sine x times 1, which is just, does that look more simple than what I started with? Yes. This whole piece, anytime you see this, it equals 1. That's as much as I could simplify it, yeah. Once you get it down to a single trig function, yeah, you're pretty much done. Let's do another. That was an easy one. Let me go back. I took it out. So think about this being like x to the third plus x y squared, and I just took an x out of. You see what I'm saying? Y'all ready to crank it up a little bit? Some of these you may not, the first time you look at them, you may have to keep working and keep working until you get where you need to get. See anything I can do. And it doesn't necessarily have to be anything trig related at first. It could be any ideas where to start? That's what I would do. That's where I would start too, Tyler. I would start exactly there. This is actually well, you'll see what happens. It's going to be a difference of 2 squares once I FOIL it out. But I would start by FOILing that out up top. I'd end up with secant squared x minus secant x plus secant x minus 1. Well, that helped a little bit, right? Because of that. I'll give you just a minute to catch up with me. Any ideas? Can't do that yet because of the subtraction up top. Okay, so you could, but then you'd have to split it into 2 fractions. You see what I'm saying? Because you'd have secant squared over sine squared, and then you still got this 1 here you'd have to deal with. So this would be a fraction, and then this would be a fraction. So before I do that, and you could do that, and maybe you do that, do you notice anything else, specifically this? Look at the Pythagorean ones. It does. Where are my? That's right, because this one, even though it's written this way, I could also write this as, I could subtract 1 from both sides and say that the tangent squared theta equals 1 minus secant squared theta, right? That's the same thing. So I could change the top of this fraction tangent squared x over sine squared. What's cosine? That's cosine? What is tangent? Sine over cosine. So let's do this. Let's do the top and multiply by the reciprocal of the bottom, because tangent, remember, if tangent is sine over cosine, let me write this as sine squared over cosine squared. But now remember, all of this is over sine squared, right? Am I confused?
Why would you do that?
The tangent, well, because tangent is sine over cosine. So tangent squared is sine squared over cosine squared. Okay, so that bottom was there. That's the bottom that was still there. If you leave that off, then you just got tangent squared. Okay? Now, so now, instead of dividing this fraction by anything, I'm going to take my fraction and multiply it by 1 over sine. All right, the tangent just became the sine over cosine. Yep, because I was dividing by that. Instead of dividing by that, I multiplied by the reciprocal because I got a fraction over a fraction. Conveniently enough, and what is that? Judging by the looks on the faces, I'm going to stop right here for today. I'm going to give you some to play around with tonight to see how it goes. We'll talk about them tomorrow, and then we'll do some a little more complicated ones tomorrow as well.